I'm Mayank, and today I will be talking about private analytics via streaming, sketching, and silently verifiable proofs. This is joint work with Yubin, Henry, and Raluca. So let me start by saying that aggregate statistics are useful, and to convince you, let me give you an example. So they are a bunch of users who have pictures of apples, bridges, and cats, and they have these tables which reflect how many pictures of each kind do they have. And there's a server who wants to learn a sum of these tables. So that would be a histogram over these pictures, and you can imagine that this sort of information could be used by a developer to optimize a Photos application that they're working on. What the users can do here is that they can send their tables over to the server, and that would satisfy the first goal we have for these systems, which is of correctness, meaning that the server should be able to compute the statistic that it wants to compute. However, there's a problem here. In particular, if the server gets compromised by an adversary, then this adversary can learn information about which users have what kind of pictures on their phone. So we do not have privacy with this approach. In particular, the server can see individual submissions of users, which is an issue. Now, this problem of achieving privacy with correctness has long been considered in systems for private analytics, and in this talk, I'll be focusing on systems which use secret sharing. So in this approach, you have two servers, one server from before, and there's a secondary helper server. In existing deployments today, the second server is run by ISRG, which is the same entity behind Let's Encrypt. So if you bring back our users from before, rather than sending the table that they had to one of these servers directly, what the users are going to do is that they will first generate secret shares. So secret shares by themselves look random. If you take any of these shares, it looks random to you, but when you bring them together, they sum up to the actual table that the users had. Users are going to share these secret shares to the two servers, and the servers are going to do some communication, at the end of which they learn the sum of these tables as they wanted to. And the nice property here is that if one of these servers gets compromised by an adversary, then all that the adversary sees is just this final table and these random shares coming from each user. So we do have privacy here, as long as at least one of the servers is honest. Now, these two challenges, these two goals of correctness and privacy have long been resolved, but many other challenges still remain with these systems, and let's look at some of them. So the first challenge that I want to draw your attention to is the communication that happens between the servers. With prior schemes, the servers need to exchange one message for each client in the system. This means that if you have many clients, then this communication balloons, and it leads to high dollar cost when you go deploy these servers on major cloud providers, and that is the first challenge. Now, there's one additional challenge. Let's say that this table that the servers were trying to compute is too large to be able to be materialized. And maybe the servers are just interested in learning the most popular entries from this table, which are called heavy hitters. Now, if the servers want to do this, then they face an additional challenge. The challenge is that the storage that they need to maintain also grows linearly in the number of clients. So we have these two challenges with prior schemes. There's many more challenges as well, but in this paper, we focus on addressing these two challenges. So now I'm going to present you the results. We propose a system called Whisper, which addresses both of these challenges. In particular, the server-to-server communication in Whisper grows sublinearly in the number of clients, and same goes for the storage. So to be more concrete, let's say there are n clients in the system. These clients are divided into batches of size B, and let's say each batch has d defective clients. What do I mean by defective clients? These can be malicious clients, buggy clients, and so on. And let's focus on the server-to-server communication rows here. For both basic statistics and heavy hitters, the story is the same, that with prior work, the server-to-server communication scales linearly in the number of clients, and what we achieve in this work is sublinear growth for appropriately set batch size. And the first term here is the number of batches, and the second term is communication per batch. Now what's interesting is that we can set batch size to be whatever we want, and if we set it to be equal to n, then one can show that the communication that we achieve is optimal. In particular, it matches asymptotically the information lower bound. So you cannot hope to achieve better than this. Now these gains do come with a small caveat, which is that we do increase client communication slightly, and I'll talk more about it in the evaluation slide later on. So this was the first challenge. But now moving on to the second challenge, which is the storage for heavy hitters. With prior work, it grows linearly in the number of clients, and what we achieve is growth with just the batch size. Now again, there's a caveat. To achieve this result, we have to allow for some error in the heavy hitter computation, although what we show is that this error tends to be pretty low, and the details for that can be found in our paper. Most of this talk will only focus on basic stats, and at the end I'll mention a few words about heavy hitters. Okay, so let's get into it. So where does this inefficiency in prior schemes, which relates to this linear scaling of the server-to-server communication, come from? It comes from the fact that there can be malicious clients in the system, and we want these clients to prove that their inputs are well formed. The way they do this is that they generate zero-knowledge proofs on secret shares, which I'll represent by these 2D objects, and they send these over to the servers, and then the servers do some communication to verify these proofs. Now the problem is that this communication has to happen for each client in the system. And this is why the server communication scales linearly with the number of clients. So how do we address this problem? We address this problem by proposing new zero-knowledge proofs on secret shares, which we call silently verifiable proofs. So the setup is the same as before, but rather than using the proofs from before, if we use silently verifiable proofs, which are slightly bigger in size, then the servers can actually do a batched proof verification. So they only need to exchange, let's say, 128 bits, and that is enough to verify as many proofs as they want. And because of this low communication is why we call these proofs silently verifiable. Now, this batch verification property actually comes from the fact that silently verifiable proofs have a very simple verification procedure. All the servers need to do is to do an equality check, which means that they'll both have a value, and if the value is the same, then the proof is valid. Let's understand this in a little bit more detail. So let's say the servers have received these proofs from 3 clients. So the server on the left has these 3 gray proofs, and the server on the right has these 3 black proofs. What the servers can do is that they can locally derive these tags from each of these proofs. So the first server derives T1, T2, T3, and the second server derives T1 prime, T2 prime, and T3 prime. And these tags are such that if you look at the first proof here, if the proof is valid, then T1 and T1 prime should be equal. And same goes for the other proofs. So normally the servers would have to communicate to check each of these tags, but what they can do is that they can compute a hash over these tags. So the left server computes this hash T, the right server computes this hash T prime, and they can only exchange these tags and make sure that these tags match. If these tags match, then with high probability, all these other tags also matched, which means that all the proofs were valid. Okay, now coming to the main question, how do we construct silently verifiable proofs? And what we show in this work is that you can actually construct them from prior proofs which do not have batch verification property. So here goes the construction. So this was the picture from prior proofs. And let's say the servers were doing some communication, and I'm going to refer to this communication with this transcript. What we do here is that we let the prover, which is the client, emulate this entire interaction of prior proofs all in its head. This is done using MPC in the head framework and a multi-party variant of Archimere. And once the client does that, it can extract the transcript of the server-to-server communication from this emulation. How does this help? the way this helps is that the client can send this transcript along with the proofs that it was already sending to the servers in the prior constructions. And this gives you silently verifiable proofs. This is the construction at a very high level. Now, how does this achieve the equality test verification property, which is sort of at the core of these proofs? To understand that, let me introduce some notation. So let's say that the servers were exchanging messages y1 and y2, and they were accepting or rejecting proofs based on a function of these messages, so f of y1, y2. And what the client was doing is that the client is, in our proofs, is the client is sending to the first server its proof as before, along with y2, which is the message that the first server should see from the second server. And similarly for the other server as well. And the client is going to send this information over to the servers. Now comes the interesting part. So each of these servers, as before, are going to use these 2D triangles, which are these prior proofs, to derive one message each. So the first server will derive y1, the second server derives y2. But the first server here is also given y2 already by the client. And same with the second server. So if we look at the second server here, it already has all the information it needs to compute this accept reject function. Which means that the proof verification for both of these servers is local now. But this is only true if we trust the client, which we cannot. We can have malicious clients which can send wrong y1 and y2. In particular here, this client is sending incorrect y2 to the first server to make the local verification pass. Now what I claim here is that in order to detect this cheating, all that the servers need to do is run a simple equality check, and that's it. And it's actually very simple why this is true. For that, let's look at the second server. So the second server already was deriving the correct y2, and an honest client was supposed to send the same y2 to the first server. So what the servers can do to ensure that the client is not cheating is a simple equality check. They can just check that the y2 that the first server got from the client matches the y2 that the second server derived from the proof that it got. And as I mentioned before, since these equality checks can be batched as much as you want, you get the batched verification property. And only equality checks are part of the proof verification where the servers need to interact with each other. Okay, so moving on to evaluation. Here I'll show you numbers for histogram with 1,000 bins. There will be 2 servers, 100,000 clients. 1% of these clients will be malicious. And I'll compare Whisper with the prior best system, Prio 3. As I hinted before, client communication and client computation in Whisper is slightly worse. So our clients incur a slight overhead. But what you gain from that is huge improvement in the server-to-server communication. So here it's 50 times better than Prio 3. And if we estimate the cost to deploy these servers on, let's say, Google Cloud, using just communication and computation as the metrics, then we estimate a 2x improvement in the deployment cost. And in the paper, we also discuss other statistics and not just histogram. Okay, so I want to spend a few more minutes talking about heavy hitters now. So if you recall from before, the servers were trying to compute the most popular items in the table. And the issue with prior schemes was that as clients come online and submit their data to the server storage keeps increasing. And the problem is that why this keeps increasing is because the servers cannot maintain a running aggregate. This is an issue with heavy hitters, not an issue with other simple stats like sum, mean, histogram. This is all from prior work. What we show in this work is that if we allow for some error in the heavy hitters computation, so if we consider the approximate heavy hitters problem, then we can uh, propose protocols where the servers can maintain running aggregate and compute heavy hitters. The main idea behind that is to use linear sketching data structures. But the tricky part is proving that the accuracy of these data structures is still maintained even when there are malicious clients in the system. And we present a new analysis which shows that you can recover heavy hitters which appear more than the number of malicious clients. So to wrap up, in this talk I presented Whisper, which is a new system for private analytics. Some directions of future work would be to improve prover efficiency, so proof size and prover time. Thank you.